Okay, so now we wanted to see that how we can implement, in fact, store this complete binary tree in memory, right? Are we going to use uh, a structure like binary search tree, AVL tree that you defined a class for node, and in each node you had two references for the left and right. Okay, definitely you can implement it like the way that we define the binary tree, binary search tree, AVL trees. But now I'm going to show you that because our tree is in a form of a complete binary tree, we can use an array to implement, to store the whole tree. How we are going to use that? Okay, just think about this example. This is a complete binary tree and this is a min heap for us as well. The way that I'm going to store this complete binary tree in an array is exactly like the way that we create the complete binary tree or the birth first traversal of the tree, which means that you visit first the root, then you visit all the nodes at level 1, so this one and this one, then you visit this one, this one, this one, this one, right? Exactly like this order, level by level and left to right. So the result is going to be stored in an array like this. So the first item will be 15, the root. The second item is going to be 17. The third item is going to be 32, 25, 19, 41, 36, 33, 55, 31, 58, 42, 89, 39, 53, and 88. So we just visit the tree in birth first order, and exactly like the way that we visit the nodes in birth first, we store them in an array. Exactly like the way that we create a complete binary tree level by level from left to right, we store it in an array. So basically, what you have in the memory is an array. But you can imagine that this array actually creates a tree like this. Okay, so basically, just to make the implementation easier, what we do is we store the items in an array and start from index 1. So this is just a minor change in the implementation, just to make sure the formulas that we get later on to access to the parents and children are going to be simplified. You can start storing at index 0, but there is not much difference between storing at 0 or 1. The only difference is that the formulas are going to be different, the later formulas, these formulas that I'm going to discuss about. And it actually makes it easier if you store from index 1. So what is going to be stored at index 0? Nothing. So we actually leave index 0 blank, and we are not going to, in fact, put any valid item from the tree in index 0. Later on in the implementation that I'll post to Blackboard, you will see that index 0 is used in some of the methods, but it is not going to be used to keep the tree. So all the items that we store, for example, if I have k nodes, 16 nodes, you will store it from index 1 to index 16, right? So in total, you are using 17 cells because the first entry is empty. You are not really using it to keep any part of the tree. So If I store my tree in an array, it means that I don't have access to that left and right references in a, remember we created a class node, and in each node you have a reference left, a reference right. So you would know that what is going to be the left child, what is going to be the right child. So we don't have a node, a class for node anymore. All I have is just an array. So how do you know, for example, if I am looking at the node 58, what is going to be the children of this node, what are going to be the children of this node, and what is going to be the parent of this node, right? These are the only references that I need to access, right? From each tree, from each node in the tree, you should know what is going to be the left child, what is going to be the right child, right? And because in the method push we are percolating up, I also need to know that what is going to be the parent. So for each node I need to know what are the children and what is the parent. If I am storing the items in an array, so I should know that if I am looking at some specific index, like for example this node 32, this is for me it is a node, but in the computer it has been stored in an array. So basically I can access to that through an index. That is going to be, let's just actually just call it, let's just put some number over this. This is going to be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Okay, so I just wanted to know that for this, for example, the value 32 that has been stored in index 3, where is the parent of this node? Where is the parent? Where is the left child? Where is the right child? I can give you a formula. So for any index, for example, index k, the parent of this value in the corresponding tree is going to be stored in index k divided by 2. This is the formula. And you can actually just simply look at that. This is going to be index 3 divided by 2. This is going to be integer division, right? So the result is going to be 1. So the parent of 32 has been stored at index 1. So now you can actually see that at index 1, actually we have exactly the value 15, the parent of the node 32. The parent of the node 32. And what is going to be the value, the indexes for the left child and the right child? For the left child, the formula is going to be 2k. So if the value has been stored at index k, left child is going to be stored at index 2k, and right child is going to be stored at index 2k plus 1. Let me actually just show you over this array. So 3 multiplied by 2, so it's this formula telling me that 41 is going to be the left child, 2k plus 1, so index 7 is going to be the right child. And look at the tree. This is exactly left child 41, right child 36. And this is not magic. Where did I get these formulas? This is a complete binary tree. So I know at each level how many nodes I have. So if I define it as level, at level 0, the number of nodes that I have is going to be 1. At level 1, the number of nodes that I have is going to be 2. The number of, so basically this is going to be 2 power the level. So 2 power 0, 2 power 1, In level 2, I'm going to have 2 power 2 nodes, which is going to be 4. And I have started storing them exactly at index 1. Now you see that why instead of storing them in the array starting from index 0, I store them at index 1 just to make, get these nice formulas, just k divided by 2 and 2k, k divided by 2 for the parent, 2k and 2k plus 1 for the children, the right and left children. This is just coming from this fact that we know this is a complete binary tree. All the levels are full except the last level. So these are the formulas. So that's it. That's just what I need when I am implementing push and pop, percolating up, percolating down. Just one more thing about these formulas. This formula of k divided by 2, 2k and 2k plus 1, these are just nice formulas that can be implemented using bitwise operators. K divided by 2, instead of, you can actually implement it by division to just get, and not only that, you can implement it using a bitwise operator. So by shifting k just one bit to the right, it's just like exactly k divided by 2. The difference between the bitwise operators and the regular division and multiplication is that bitwise operators are going to be much faster than the regular division and multiplication. Although over the nowadays, using these fast computers that we have, this is not going to make a big difference for us in regular basis. But if you have implemented priority queue that works over a large amount of data, even moving from a regular division and multiplication to just bitwise operators, that makes a difference in the efficiency. So to implement actually multiplication, multiplying by 2, you can shift k to the left by just 1 bit. I think you are familiar with the bitwise operators. If not, please just search online. It will actually show you that how the bitwise operators shifting the the bits in the memory are going to exactly just show you if you shift to the left, you are making it bigger. If you shift to the right, you are actually dividing the value. If you shift 1 bit, divide by 2. Shift 2 bits, divide by 4, and so on. And how to get the 2k plus 1, shift and then OR with 1. It can actually just shift to the left by 1 bit and then apply the OR operator, which is going to be a bitwise operator again. This is exactly why we started storing the items at index 1 instead of index 0. If you store the item at index 0, these formulas are going to be a little bit different. Just take it as an exercise. Try to think about storing the items starting from index 0 instead of index 1, and then find out what is going to be the formula for parent, what is going to be the formula for the left child, what is going to be formula for the right child. So let me just go over a couple of examples to just make sure that you get the idea and you get used to this array implementation of the tree, because here we don't have the class node for one class for tree, one class for node separately. We just have one array. Okay, so in this array I have stored the root at index 1. So if I'm looking for the children, I should look at index 2k plus 1, right? So if the value that I'm looking is at index 1, the left child is going to be 2, the right child is going to be 3. indexes 2 and 3. If I have, this is going to be index 2 in the tree, right? So where are the children? The children are going to be at index 4 and at index 5. So 25 and 19. Where are the children for this node? This has been stored at index 3, so the children are going to be at index 6 and 7, 2k and 2k plus 1. For this node, the node has been stored at index 4, so the children are going to be at index 8 and 9, 33 and 55. Okay, so in our implementation, we have an array. What else I'm going to keep? I'm going to keep just one variable, one data field, integer data field, that tells me how many items has been stored in this array, how many items are in this complete binary tree. So we are going to actually just need another variable. Let's just call it count. It tells me that, for example, if I have 5, because you know that the size of the array, implementation wise, the size of the array is something fixed that you get it in the constructor. But then, for example, assume that you just have 5 items in your array. So those items has been stored at index 1, 2, 3, 4, 5. So the rest of the indexes are empty, right? So just assume that you have actually filled 5 items already, so that what you have stored is something like this, but the tree would look like this. Then you wanted to actually insert how many, you have one array, this array, and you have a variable count, which is going to be, for example, 5. Then you are going to add a new value. Remember, we added it as the last leaf node. So it is going to be in the tree. This is going to be here, where it is going to end up in the array. So whatever is count plus 1 is going to tell me the position of this new leaf node. So this is going to be the position. That's why I need to keep track of the count. Okay, you put the value there, then you can actually percolate the item up. How to percolate up? You need to compare with the parent. What is the index for the parent? Whatever the index that you are in divided by 2, it gives you the index of the parent. So look at this heap and just assume that we are going to insert a new value to this heap, like for example the value 26. So how many items I have in my heap? What is the count? You will see that I have 11 items. So where I should put the new item, just assume that I'm going to insert to push 26 to this binary heap. I know that if I had a tree, this is going to be the position for 26. Okay? But where in the array I should put it? I should put it at count plus 1. So that is going to be the index 12. So you put 26 here. Then we have to actually percolate up this value, because we don't know what is the value. It might actually be a very small item. You have to compare it with its parent. So you have, where is the parent of this node? You are at index 12. Where is the parent? So 12 divided by 2, it gives you the parent, which is going to be at index 6. You compare it and you will see that, okay, the value at the parent is smaller, and you would stop. So that's it, 26 will be inserted at index 12, and you would stop percolating up because the parent is already smaller. This is actually just showing you the procedure. Then assume that I'm going to, okay, one more example. I'm going to insert a new item like 8, where I have to actually put 8. Remember the previous value of count was 11. After one push, count now is 12. So where I should put the item, the value that I'm going to insert is 8. Where I should put it, at count plus 1. So at index 13, I will put 8. So in the tree, it is just like you put a new leaf node and it is going to be 8. Then you have to percolate this value up. You have to compare this value with its parent. Where is the parent? The parent is going to be at 13 divided by 2. So 13 divided by 2 is going to be 6. The value 13 will be compared to, the value at the index 13 will be compared to the value at index 6. Is it smaller than the value at value of the parent? Yes, it is smaller, so you have to swap them. Okay, it's actually just showing you here. Then you have to swap these two values. Then 23 will be actually end up here, right? And 8 will end up here. Then still you have to actually go until you stop. So you compare the value at index 6 to its parent. You are at index 6. You have to compare with its parent. Where is the parent? Parent is going to be at index 3. So you compare 8 with 12. It is smaller, so you need to swap them. It will look like this. Then you have to continue. What is the current index? The current index is 3. You have to compare with the parent. Parent is at index 1. So index 3 and 1 will be compared. 8 is greater than 3. So you will stop. So you compare these two, and because 3 is already smaller, you would stop percolating up and 8 will stop here. This is going to be the shape of the your array after you are done with 2 push. We push 23 and 8. I showed you this tree, but the tree doesn't really exist. What you have is just this array and a variable which we call it count, which already is going to be 13, right? How many numbers I have, how many items, how many nodes I have in this binary heap that has been stored in this array, 13, and this is the array. So now let's actually just see that how we can implement pop. Remember when we were going to implement the pop, the value with the highest priority should be returned. So 3 should be returned. But before I return the value 3, I have to make sure that the result is going to be a complete binary tree. So remember we removed the last leaf node. What is the last leaf node? This one. And you have to actually just copy it to the root position and then percolate it down. So we don't really have the tree in this shape. I only have an array. But I know where is the index of the last leaf node. Whatever count is, this tells me the index of last leaf node. So I need to actually look at this index 13. I need to copy it to the root index, where the root has been stored at index 1. So the first thing that I need to do is just copy that value to the index 1. After you actually do that, you have to decrease the count as well. The count is going to be 12 because you already removed this node, right? This is going to be, okay, you keep the 3 somewhere in some temporary variable, then you copy the value at index count to index 1, and then you decrease the count. So count now is 12. Then I have to percolate the value 23 down because this is probably a large value because you copied from some leaf node, right? I have to percolate it down to make sure that this is going to be a binary heap, a min heap. So to do the percolation, to percolate down a value, you have to compare the value with its children, left and right children. So the current index is 1. You have to compare to the left and right children. So left child is going to be at index 2k. So this is going to be 2. The right child is going to be at index 2k plus 1. So this is going to be to index. So you have to compare it, this one and this one. Whatever children is going to be, which of the children is going to be the smaller one, that should be copied to swap to the parents. So you can see that at index 2 and 3, the smaller one is at index 2. So you swap these two, or you swap at index 1 and index 2. Then this 6 and 23 will be swapped. So 23 will now be at index 2. You have to actually keep going and percolate it down. You need to compare it with its children. Where are the children? 2 multiplied by 2, 2 multiplied by 2 plus 1. So they are going to be at indexes 4 and 5. You compare these two values, whatever is going to be smaller, 9 is smaller, so you have to swap the index 2 and index 4. Right, you swap them, so now 23 is going to be at index 4. Index 4. Where are the children? 2k and 2k plus 1. So you need to compare index 4 with index 8 and 9. Between index 8 and 9, which one is smaller? Index 8 is smaller. The value at index 8, 10, is smaller. So you have to swap the index 4 and index 8. So now 23 will be at index 8. So I need to still compare it with its children. So what are the children? The children are going to be at index 2k and 2k plus 1, which is going to be at index 16 and at index 17. But are there any children for this index 16 and 17? In fact, if you think about the tree, there is no children for this node. This is going to be a leaf node. But how do I know these indexes are empty? I know because currently the value of count is equal to 12. So whatever the index greater than 12, this is going to be, out of the tree. So both the indexes 16 and 17, both of them are out of the tree. You would stop because it's just like 23 is at a leaf node. So this is going to be the result after one pop. Let's just apply another pop to just make sure that you get the idea. If I call the pop again, what would happen? I would actually take 6, copy it somewhere. I need to return 6, and then I will copy the last leaf node of the tree. Where is the last leaf node? Remember, the value of count was 12, so I have to look at the index 12, copy it at the root position, which is at index 1, right? Copy it here, and then I need to percolate down. So it's just like currently the index of the value is 1. I need to start percolating down. I need to compare at the children, which are at index 2 and 3. Compare the values at index 2 and 3. Which one is smaller? The value at index 8 is smaller. So I have to swap 26, the index 1 and index 3. So now the current index of 26 is index 3. Okay, then I have to look at the children of this index, which are at index 6 and 7. So you have to look at indexes 6 and 7. Compare them. Which one is smaller? The value at index 6 is smaller. So you have to swap index 3 and index 6. So 26 will be copied at index 6, right? Then remember, when we actually copied the value here, let me actually show you again. When you copied the value at the index count, you need to decrease the value of count immediately. Why? The count will be actually 11. So to make sure that this index is out of the tree, this is not in the tree anymore. So when you copied this value, you immediately have to decrease the value of count to make sure that later on I'm not going to actually make any error. So you are at index 6, you wanted to look at the children. So you are at index 6. Where are the children? At index 12 and 13. So, but what is the value of count? The value of count is 11. Both of these two values are greater than count. Then it means that so already the index 6 is a leaf node and there is no children for this node. So you would stop percolating. So the tree will stop, the procedure of percolating down will stop here. This is the result. If you look at the array is in fact a binary heap, a min heap. So let's just apply the pop one more time. Again here, what was the value of count? The value of count was 11. If you wanted to actually pop, you copy the root somewhere, then you copy the value at index 11 to index 1, then decrease the value of count as well. So count will be 10 now. Then you percolate down. So you started from index 1. Where are the children? At index 2 and 3. So you compare the index 2 and index 3. Which one is smaller? The value at index 2 is smaller. So you have to swap the value at index 1 and the value at index 2. Now the current value, the current actual index is going to be 2. Where are the children? At index 4 and at index 5. You have to compare the value at index 2 with the value at index 4 and the value at index 5. Which one is smaller? The value at index 4 is smaller. So you have to swap the index 2 and index 4. So this is the result. Now the index is going to be 4. Where are the children? At index 8 and index 9. Okay, you see that in all of these cases, still the index is smaller than count. So these indexes are valid. These indexes are in the tree. Okay, so you compare the value at index 8 and index 9. Which one is smaller? The value at index 8 is smaller. Then you compare it to the value at index 4, which is the value that we are going to percolate down. But this is, even the smallest children is not smaller than the value that you are percolating down. So you would stop. You are not going to continue because 15 is already smaller than 23 and 25. So here you would stop. You didn't reach to a leaf node. Here you have stopped. And this is going to be the result. Still, this is a binary heap. This is a min heap. And this is a complete binary tree after a couple of push and pops. This was the original tree that we had, and after actually a couple of push and pops, this is going to be the result. So already we know that the time complexity of top was constant, right? Because basically, where is the top? This is going to be at index 1. So just look at index 1, whatever is that, you return it. So the time complexity of method top is, or peak, is going to be constant. The other method that we have was pop. Remember, what was the pop? Pop, you actually copied, you get the root out, you copy the last leaf node, copy it at the root, then you percolate down. Basically, for the method pop, it is very clear that the time complexity will be the height of the tree, because usually the value that you copy from the last leaf node is going to be one of the largest items in the tree, because this is going to be a leaf node. So if it is a leaf node, it means that it is bigger than all of the nodes starting from the parent to reaching to that node. So leaf nodes, all the values that is stored at a leaf node in a binary heap, in a min heap, are going to be the largest items in the tree, right? So definitely the time complexity of pop is going to be theta of h, which we already know that because this is a complete binary tree, this is going to be theta of log of n, or O of log of n. How about push? Remember how we did the implement the method push? Let me just show you, do one of those examples, show you one of those examples. Remember that this is going to be a better actually example. That you started, we wanted to actually insert to 26, right? You put it at the last, whatever is count plus 1, right? And then you percolate up. But how many steps you would percolate up? If the value that you are inserting is a very small value, for example, if in this case I was inserting something like 1 was the smallest, 1 is smaller than even the root, right? So definitely the percolating, these steps of percolation would took until reaching to the root. But what if I am inserting some large item like 26? If I insert 26, you wouldn't even do one step of percolation, right? You just compare 26 with its parent, this is bigger, and you stop. So you see that in the best case, this is going to be constant, best case. If I am inserting a large item, if push a large value, and worst case you would reach to the root. So the worst case you would get to log of n, the theta of the tree, right? And what is the worst case? The worst case is that you are inserting if you push a very small value. But there is a difference between the best case and the worst case for us here. Usually if the best case and the worst case are different, we have to also take a look at the average case. If I randomly just insert a value, how many steps you would percolate up? Okay, so for example, if you randomly, just think about a simpler problem. Just if you have a regular array, I'm not talking about the binary heap at all. I'm just trying to actually give you this sense of the best case and worst case for the time complexity. If you are inserting some item in an array just randomly somewhere here, you have to actually here, you have to push the items to the right to make some space and insert. How many items in average you would actually insert? To calculate that, you would actually consider that what if I insert at index 0, what if I insert at index 1, 2, 3, 4, until at index n. The number of shifts you calculate them, add them all, so it's going to be, if you insert at index 0, you would need the number of shifts, so you would need n shifts. If I insert at index 1, I would need n minus 1 shifts. If I insert at index 2, I would need n minus 2 shifts. If I insert at index n, I would need 1 shift. So basically this is going to be the summation of all these numbers until 1. So this is going to be the summation of all the numbers from 1 to n. This is going to be n to n plus 1 divided by 2. So this is going to be the total number of shifts. You divide it by n. The result is going to be theta of n. So on average, I would say inserting at some arbitrary position is going to be linear in a regular regular array. What is going to be the average time complexity if I push an item to a binary heap? I don't know if this is going to end up to constant or log n, so I need to calculate it. How I am going to calculate that? I wanted to actually just again do exactly the same analysis here. What if the value that I insert is going to, for example, what if the value that I insert is going to stay here? What if the value that I insert, it ends up to this level? What if the value that I insert, it actually needs to percolate up until this level? What if the value that I insert, it ends up to this level? Okay, so I would just calculate all of these, get the average, and this is going to be the time complexity in the average case. When you have a difference between the best case and the worst case, you need to calculate the average case. So to do this calculation, what I'm going to do, basically I'm interested in this case because maybe the average case can be less than log of n. And even if it is the case, that would be great. You can actually get some implementation that on the average, even inserting to your priority queue can be less than log of n, and that's great. How can I calculate the average time complexity? So you can think of it as, just assume you have a tree. This is your binary heap. Until this level. And just assume that I don't know how many levels. So in general, I can actually just think that you have h plus 1 different levels. This is going to be at level h. This is going to be at level 0. Okay, so just assume that you have added a new item. That the item that you have added, how many, on average, it is possible that it actually end up to one of these leaf nodes, right? So if in total I have 2 power h plus 1 minus 1 nodes in the tree, for 2 power h of those values, the number of percolation is going to be 0, right? So if you randomly just choose an item and insert it in your tree, it can be actually a large item. So 2 power h divided by 2 power h plus 1 minus 1 chance, it can end up to here, one of these nodes. Okay, and so for 2 power h minus 1 node, it can actually end up to this level. And, you know, I just wanted to actually give you this idea that it is very, less possible, less probable that the value that you insert to your tree end up to the root than end up to a leaf node. Okay, most of the case, the value that you insert is going to end up as a leaf node or end up at this level or this level or this level. And only in a very few cases you would end up to the root node, or you would end up to actually at level 1 or level 2. But to be precise, how can I calculate in average? I would say that how many items I have at the level 0. At level 0, I'm going to have 2 power 0 number of leaf nodes. How many nodes I have at level 1? It's going to be 2 power 1. How many nodes I have at level 2? 2 power 2. How many nodes I have at level 3? 2 power 3, and so on. So this is going to be the total number of nodes, which is going to be 2 power h plus 1 minus 1. And for each of these nodes, how many steps of percolating up I need? If you insert a value like the value that you have at the root, you have h number of percolation. You have to percolate up to the root. So the number of steps of percolation is going to be h. How many steps of percolation you need? Percolation steps. This is going to be h. But for 2 items, if you insert something like this node or something like this node, the number of percolation is going to be h minus 1. If you insert some item like the one at this node, or this node, you would need h minus 2 number of percolation. So in total, if I wanted to calculate the number of percolation for all the nodes, I just need to multiply all these numbers, the number of nodes to the number of percolation steps that I need to apply and get the average. So the result of this is something that we have done when we talked about the perfect, the average depth of the perfect binary tree as well. This is very similar to that. If I do this calculation and the summation, if you add all of these numbers, multiply them and add them all, the result is going to be something like s. I don't want you to actually to memorize it. Just know that this is going to be 2 power h plus 1 minus 1 plus h plus 1. And so in total, this is going to be, know that the number of nodes is going to be 2 power h plus 1 minus 1. So I would say that in a complete, in a binary heap with n nodes, the number of percolations that you would need on average for all the nodes is going to be n minus h minus 2. So if I take the average, you would divide it by n, right? And yes, ta-da! I got the average time complexity of constant for the push. You see, it tells you that if you randomly take an item and insert it in your, push it into your binary heap, which has been stored as a complete binary tree, the time complexity of the push, the number of steps that you need is going to be constant. If you take some random number, on average, the time complexity is going to be constant. And actually, this is very nice. So in total, I have actually ended up to these time complexities, that the time complexity of just checking the pick is constant. The time complexity of push, in the best case, is constant. In the average, is going to be constant. Just in the worst case, it can be log of n. And the time complexity of pop is going to be log of n as well. Instead of all these O's, you can actually write theta as well. There is no difference. These two actually cases are very special cases. If you have to, basically they are very useful if you are taking some interview questions or something like that. I don't want you to know it as a part of the course, but just know that if you have two binary trees stored as a, if you have two binary heaps stored in a form of a complete binary tree in two arrays and you want to merge them, the time complexity and the size of both of them are n, the time complexity of merge is going to be theta of n. And if you are going to just remove an item from your binary heap, from your array, which is a binary heap, just randomly take an item and remove it, not pop, just randomly take one of the items. Just assume that this is a binary heap and you, for example, remove this one. Okay, to make sure that this is still a binary heap, you have to, the time complexity of removing a random item is going to be theta of n. This is different than pop. Pop only remove the one with the highest priority. Pop will remove the root value. Okay, so this is different. Just take them as a part of, these are usually the trick question in the interview for coding. Usually when we talk about the priority queues, we need, in fact, 3 more methods to add. The first 2 ones are about changing the priority score for some items which are already in your priority queue. Think about it in this way, that you have inserted a couple of items into your priority queue, and then all of a sudden the priority score for one of those items has changed. For example, you assigned it a better score. It for example, if you are you have a min heap, the item is going to have a smaller score. Okay, so it means that everything has been changed. For example, just think about it in this way, that you have a priority queue, a binary heap in this form. Like, let's say this is 3, this is 5, this is 7, 10. Here I have something like 9, 12, and 15. Okay, and then the value here has been changed, the score for that has been changed to, for example, I know, for example, 2. Very good. So it's just like the score for this number has changed, and you are in fact decreasing the key in your min heap, right? The value, the key has been decreased. This is a min heap. If it was a max heap, you should actually think about it as increase the key. So if the score is going down or going up, there is difference. If the score is going down, so the value is 2, you have to in fact percolate your value up. So let's just use a different color. So if the value, the key here has changed to 2, you have to keep percolate it up, right, until it actually end up to correct position. So it's possible that you, you know, the score of some of the values, some of the items in your priority queue would update. So you increase the value or decrease it. Or for example, you might actually change the score of some numbers. For example, the score of this one became 8. In this case, you have to percolate it down, right? So we need 2 more methods. One of them is called DecreaseKey. So DecreaseKey, if you have a min heap, so this is going to be a min heap. So decreasing the key means that you increase the priority of that item. So you have to percolate it up. So you need one method, but that basically actually just, let's just call it DecreaseKey, and it will percolate the values up. And if you change the values and increase the key, so it's just like the 5 that has been changed to 8, you decrease the key, but because this is a min heap, it means that you increase the key, but it is going to decrease the priority, so you have to percolate it down. So I think this is clear that how to implement these methods, because they are basically just percolate up and down. And the last method is build heap. Just assume that someone gave you n items and he wants to create a priority queue from all of these items. So the items are given to you as an array, right? And n items in an array, and you wanted to create a priority queue from these n items. One way to do it is just create a priority queue initially empty. So this is going to be a new array. This is initially empty, and you just push all of those items one by one to this new priority queue. The time complexity, because you don't know the order of the original items, can be actually go with the worst case, and you have n numbers. The worst case of the push is going to be log of n, so in total the time complexity is going to be n log n. Not only that, you can see that all the items is given in an array, and you are creating another array, right? So the operation is not in place as well. Now I'm going to give you an algorithm that creates a priority queue over this array in time complexity linear. And not only that, that's linear, but also it just doesn't actually use a new array. It will create a priority queue over the original array that is given. The idea is that we can assume that the original array that is given to us was a priority queue before, and someone just changed the order of some of the items, so this is not a valid binary heap. This is not a valid min heap anymore. But the idea is that we can assume this was a binary heap, this was a valid binary heap, someone made some changes, we wanted to find them and fix those issues in our binary heap. So how we can do it, you can actually think of it, let's do it over an example, actually. That makes it more, easier to understand. This was the original array which is given to us. Okay, you have all these items in your array, and you can think of them as a binary heap. So this is going to give us a tree like this. This is actually stored as an array, but you can think of it as it was a tree, right? It was a binary heap like this. How I'm going to fix the issues? I can just, for each item, check that if the item is smaller than its children, we are done, right? If for all the items, the item is smaller than its children, it means that the full array is a valid binary heap. If not, we percolate that item down. And we started from the end of the array. Actually, we started from the end of the array, from the last item, and you go up. So for each item, you just compare it with its children. If it is smaller, don't do anything. If it is larger than its one of its children, it will you just actually percolate that value down. So for all of the leaf nodes, basically you don't need to do anything, right? You just skip them, all of the leaf nodes. So basically it's going to end up until here. You don't do anything for the first half. The second half, because basically all of those items are going to be the leaf nodes, right? They don't have a children. It's not possible for them to be smaller than the children. Then for the rest of the items, just one by one, you compare it with its children. If it is smaller than the children, this is a valid min heap. This node comparing to its left and right children, it is smaller, don't do anything. How about this node? Comparing to the left and right children, no, this is not smaller than both the children. It is not smaller than the leaf node. What I'm going to do is that I will percolate this node down. Okay, so you percolate this node down, so you swap these two. This node will actually swapped, and 15 will actually go up here, 17 will go down. For this node, this is already smaller than the left and right children, so you don't do anything. And for this node also, this is not smaller than both left and right. The right one is smaller, so you percolate this node down as well. So you swap these two. So the result is going to look like this. Okay, we are done with all the nodes at this level. Then you go and process this node. So for this node, is it smaller than the left and right subtree? The left and right children? Yes, it is smaller, so you don't do anything. How about this one? Is it smaller than the left and right children? No, this is not. And you have this node, which is smaller. So what I need to do is I need to percolate this node down. Probably it was not a good idea to just remove that. Okay, we percolate AT down. So what would happen is AT will actually percolate down. You will see that not only it actually copied here, and 10 will be copied here. Then you have to actually keep going and percolate down. 80 will end up here, and 60 will be here. So this is going to be the result. Then you actually do the process for the last, or basically the first index, the root. You compare it with its left and right children. If it was smaller, it would be just a complete binary heap, min heap, and we are done. But it is not. It is not smaller than the left subtree. So you percolate 150 down. It will actually percolate down here. Then it will actually swap with 150 here. 10 would be here. Then 150 is smaller than sorry, greater than the left child, again it will be actually copied here, 20 will be copied here, and you continue percolating them. Compare this node with its left and right subtree. The right subtree is smaller, so you swap these two. 150 will end up here and 30 will end up here. So this is going to be the final shape, and you are done. Okay, so you see that I didn't really need to create another array. The original array which is given, I just change it, do a couple of actually fixes, and the result is valid min heap. What is the time complexity? So you saw that what we did was just checking each node, and for each node, if it is greater than the left or right subtree, you started actually percolating down. Okay, so for some of the nodes, we did the percolation down. What is the cost of the percolation down? The cost of the percolation down is going to be the height of the node. Okay, so what is the time complexity for the total procedure that we did? It is going to be the height, the summation of the height of all the nodes. So I just need to get the summation of the height of all the nodes. And you can actually see that what is the height of the leaf nodes? The height of all the leaf nodes is going to be 0. Remember, we didn't actually check the leaf nodes. We already assumed that, okay, if it is a leaf node, it doesn't have a left or right subtree. We didn't do anything for the leaf nodes. And then for all the nodes at height 1, we did at most one percolation. And for all the nodes at height 2, we would need 2 steps of the percolation. And for this node, we would need 3, right? So just get the summation of the height of all the nodes. So that is going to be the summation of, okay, I have how many nodes I have at the last level. If the tree has height h, I have 2 power h nodes at this level. I have 2 power h minus 1 nodes at this level. I have 2 power h minus 2 nodes at this level, and so on. Okay, again, we are actually referring back to that summation, that how many nodes you have at this level, multiply by the height of that, multiply by the height, multiply by the height. So this was going to be exactly the same summation that we discussed for the time complexity of the push. This summation is going to end up to this formula. We already know that 2 power h plus 1 minus 1 is going to be the number of nodes, which is going to be n. So in total, the time complexity that you have is going to be n minus log n. So this is going to be in theta or O of n. Little n or big N, doesn't really matter which one, right? Okay. So we are done. Our algorithm to build the heap not only doesn't use additional space for the memory, does it in place. The time complexity for that is going to be linear as well. This is very important because basically when we talked about the sorting algorithms, we will see a sorting algorithm that is called heap sort that use a binary heap, and the build heap is very important for us, and the time complexity of that because build heap can create a heap out of an array in place and in linear time complexity. It makes it very efficient, and the algorithm is in place. We don't use additional space. So this term in place, I know you probably haven't heard about it. We will talk about it when we talk about the sorting algorithms. So everything that we have discussed in this lecture was about min heap. So you can in fact create a max heap by just changing the order of all the operators that you did. So this is going to be this example here that you can see is going to be a max heap. If you look at every node, the item at each node is greater than the every item at the subtree, every item which are in the corresponding subtree. 29 is the largest item in the tree. 23 is the largest item among all these items. 26 is the largest item among all these items. 15 is the largest item among all the subtree behind that, which is nothing. For example, 9 is the largest item among all the nodes under 9. 25 is the largest item among all the nodes. So you see that the max heap and min heap are very similar. Everything that we talked about the implementation, if you just reverse the order, you get a max heap instead of a min heap.